Should we start? Or
I'm happy to wait, like, if you want.
let's say like 1 more minute, if anyone's in the road, one way.
Will you wait until 35?
What?
Wait until 35?
You should start at 35, okay.
Yeah. Shall we start now?
Sure. Okay,
Should I section? Introduction.
sure.
Hi everyone, we have Saachi Mutreja from Columbia visiting today. She's going to be talking about classical obfuscation of quantum circuits by public verifiable QFHE.
Okay. Is the camera okay, or should I?
What?
Is the video okay, or should I move it?
I think it's
Okay. Okay, yeah, so I'll be talking about classical obfuscation of quantum circuits via publicly verifiable QFHE. And this is joint work with James, Aparna, and Omri. So I'll start by first talking about what classical obfuscation is and what we know about classical obfuscation. So in this setting, we have a classical circuit C, and the goal is to scramble the code of the circuit while maintaining its functionality. So what is a classical obfuscator? You can think of it as a one-way compiler. And the job of this compiler is to render code unintelligible without harming functionality. And why is this useful? It's useful for protecting software, protecting against intellectual property theft, and so on and so forth. And certain notions of obfuscation, like indistinguishability obfuscation, which briefly says that if two circuits are computationally, if two circuits are functionally equivalent, then their obfuscations are computationally indistinguishable. This type of notion or primitive, it's considered crypto-complete. So it's so strong that it can be used to construct public key encryption, fully homomorphic encryption, functional encryption, etc. And classical obfuscation is known to exist from standard assumptions. And there are also candidates for classical obfuscators that are secure against quantum adversaries. So post-quantum candidates exist. Okay. So what about quantum circuits? This talk is about obfuscating quantum circuits. So you can think of a quantum circuit as a series of gates and measurements. And we have a classically described quantum circuit, which you can just write out the gates. So apply the H gate on the first qubit, apply the T gate on the second qubit, so on and so forth. So you can classically describe this circuit, this quantum circuit. And then we also have quantumly described quantum circuits, which can be thought of as quantum circuits with some auxiliary state or some like auxiliary quantum state as advice. And we'll be talking about classically described quantum circuits. So whenever I say quantum circuit, for the rest of the talk, I mean this type. Okay, so again, the goal of quantum obfuscation is we start with some quantum circuit Q, and we want to come up with an algorithm that takes as input this quantum circuit Q and outputs a circuit Q tilde, which is maintains Q's functionality, but none of the code is intelligible. So there's been a long line of work. By the way, feel free to interrupt with questions. There's been a long line of work on quantum obfuscation, and the central question that all of these works have been trying to answer is assuming that we have ideal obfuscation of classical circuits, meaning assume that you basically get classical oracles for free. So assuming this, what can we say about ideal obfuscation of quantum circuits? And this is this is why all of these results are in the classical oracle model, because what ideal obfuscation says very briefly is that whatever an adversary can do with an obfuscated circuit, it can also do with just oracle access to the original circuit. So assuming that such a primitive exists for classical circuits, assuming classical obfuscation, assuming a ideal classical obfuscator, can we get ideal quantum obfuscation? So these are all the works, and like a key feature or like a rather undesirable feature for most of these works is that the obfuscated circuit, meaning Q tilde, it has a quantum description. So this means that the obfuscating algorithm, which takes as input some quantum circuit and wants to obfuscate it, this obfuscating algorithm, it has to be quantum. And one justification for this could be, okay, it could be that the obfuscator takes as input quantum circuits that have auxiliary quantum states. So it's valid for the output to also have a quantum description. But this is also the case for this work that we'll be focusing on today, which is BKNY 23. In this work, they obfuscate classically described quantum circuits. So quantum circuits where you can classically describe them. They obfuscate this class of quantum circuits such that the output or the obfuscated circuit has a quantum description. So pictorially, like you start with a quantum circuit that you can describe classically, then you obfuscate it, and you end up with some circuit whose code is unintelligible and plus a quantum state. So this is not really a desirable feature.
Question.
Yeah.
So which kind of circuits cannot be described classically?
With those that come with quantum advice.
Oh,
Or like this doesn't come with any quantum advice. It's just you can just write out the gates classically. So yes. So in particular, this result, BKNY23, it takes as input quantum circuits that can be classically described, and it obfuscates them so that the obfuscated output is some circuit that's classically described but unintelligible plus a quantum state. So the obfuscation output is quantum, even though the obfuscation input was classical.
Okay.
So this is undesirable, especially if you compare it to what happens in the classical case, where you give some classical circuit as input and you obfuscate it, and then you get another circuit. This is sort of not too desirable. So the main question we ask in this work is the following: is a quantum obfuscator necessary to obfuscate expressive classes of quantum circuits? And answer is no, actually, because our main result is that assuming that this learning with errors assumption is hard for quantum computers. In the classical Oracle model, there's a classical obfuscator for pseudo-deterministic quantum circuits.
So for example, so like what is a quantum device?
Sorry?
So like, for example, so like what is like a quantum device?
Quantum device.
Yeah, so like, so not classical, like this one, so like you mean, so like in a.
It's like quantum advice, not device.
Yeah, like a quantum state that comes with the circuit.
Oh.
Yeah. Okay, yeah, so our main result is to construct a classical obfuscator for pseudo-deterministic quantum circuits. And what are pseudo-deterministic quantum circuits? You can think of these circuits, these quantum circuits that take some classical input and they map each input to a fixed output with high probability. So in particular, these are not sampling circuits, so the output is not distributed over some distribution. It's going to be fixed with very high probability for every input. And for these classes of quantum circuits that are classically described, we construct a classical obfuscator. So we construct a obfuscating algorithm which takes in classically described pseudo-deterministic quantum circuits and outputs a classically described, like a classical output. Okay, and this is actually pseudo-deterministic quantum circuit. This class of quantum circuits is very expressive. So it actually captures all quantum algorithms for problems in NP. In particular, like the factoring algorithm, Shor's algorithm, falls in this class. So it's a pretty expressive class. Okay, yeah.
So I guess I'm getting a little bit ahead, but like is LWE crucially needed here because you already have like classical oracles? Maybe you do like unconditional constructions instead? Let's try it.
So LW is definitely needed for the QFHE Mahadev's scheme.
Right. I guess you could plausibly get unconditional using oracles, right? And possibly.
I haven't thought about that.
Maybe you need to prove the FHE into the obfuscator.
Yeah, I mean, I guess using, ideal oracles, you can get an FHE scheme unconditionally, right?
Yes, but in that case, you cannot put that FHE into obfuscator. Because that use the oracle, use the ideal obfuscator.
I see.
Okay. Okay, so how will we construct? So our goal is to classically obfuscate quantum circuits. Our goal is to get classical obfuscation of quantum circuits. Oh, sorry. And we will do this by constructing a primitive, which is called publicly verifiable QFHE, which is quantum fully homomorphic encryption with the classical client. I will explain everything. This is and we will construct publicly verifiable QFHE from commitments to quantum states with public decodability with classical keys. This is a mouthful, but it will be clear soon what all of these primitives mean. So just to draw some parallels between prior work. So there's this work that I said, this BKNY in 2023, and they constructed quantum obfuscation of quantum circuits. That was their main result. And the way they did that is by constructing publicly verifiable QFHE with a quantum client. And how they get publicly verifiable QFHE with a quantum client is by constructing commitments which satisfy some notion of binding. But these commitments, the commitment keys are quantum. So essentially what we're doing in this work is we're just dequantizing this result. Does that make sense? Okay. So first, I'll talk about how publicly verifiable QFHE with the classical client, if we had this primitive, how it would give classical obfuscation of quantum circuits. So I'm sure you know like fully homomorphic encryption, but I'll give some like background. So what is a FHE scheme or a fully homomorphic encryption scheme? Very briefly, the idea of an FHE scheme is that there's a classical client and there's a function it wants to compute, but it wants to outsource computing this function to the server, to another party, a server. And it wants to outsource computation of this function, but it doesn't want to reveal its inputs. So it wants the server to compute a function f on some inputs while not revealing what inputs it wants the function to be computed on. So very roughly, that's the goal of FHE. And so more concretely, we have this classical client, which generates public keys and secret keys. And say it wants to encrypt a function f on some input x. So it encrypts the input x with the public key. It gets a ciphertext, and then it sends the ciphertext to the server, who will run the evaluation functionality. This is some functionality that is part of the FHE syntax, and the server runs the evaluation functionality, and it gets CT prime, which is another ciphertext. And like the magic of FHE is that when the client decrypts this ciphertext CT prime with the secret key, it actually recovers f of x. So it outsourced computation of the function f on input x to the server without revealing its input. And that's because CT prime, the correctness guarantee of FHE, says that when you decrypt this encrypted output, you end up recovering the true output. Okay. And so for this talk, because we're talking about quantum circuits, we will need quantum fully homomorphic encryption. And this is exactly the same as just classical fully homomorphic encryption. But now instead of wanting to outsource computation of a classical function, the client wants to outsource computing some publicly known quantum circuit to a server. So there's a publicly known quantum circuit, and because the client is classical, it wants a quantum server to compute this circuit on some inputs that it doesn't want to reveal. So what it does, again, same thing, encrypts the input, sends the ciphertext, and then this quantum server will run the evaluation functionality on this quantum circuit on the encrypted input. And the classical client can recover Q of X just by decrypting CT prime with the secret key that it sampled in the beginning. So this is the same, but now we're evaluating quantum circuits. And this primitive, quantum fully homomorphic encryption, Mahadev in 2018 constructed this, again, assuming the post-quantum hardness of learning with errors. So assuming LWE, we have QFHE schemes with classical clients, quantum servers. So, okay, so now you believe me that there are QFHE schemes. Assuming I have a QFHE scheme, how will I try to obfuscate a quantum circuit Q? So QFHE is about hiding inputs, and the goal of obfuscation is to sort of hide the code of a circuit. So a natural thing I could try to do is I could try to recast the circuit Q as an input to another circuit. So what I could do is I could recast Q evaluating on input X as evaluating some universal circuit U on Q and X. So what a universal circuit does is that it takes as input a description of a circuit, and it evaluates that circuit on the input X it's hard-coded on. So now Q is an input to use of X. And now potentially I can try to encrypt this input or encrypt Q using QFHE. Yeah, that's one natural approach to obfuscation. This also appears in classical literature. It's quite folklore. Okay, so what will the obfuscator do? It will run the QFHE key gen procedure. It will get public and secret keys, and then it will encrypt the circuit queue with this public key to get CTQ. And then the CTQ is my obfuscation output. So the obfuscator outputs CTQ as the obfuscated circuit. And the evaluator will run the universal circuit, which is hard-coded on X, on this encrypted input, CTQ. And it will recover CT prime. So does anyone see what's like missing here?
It's still encrypted.
Yeah, exactly. So it's still encrypted, but I cannot, but the obfuscator cannot just release the secret key in the clear because the secret key encrypts Q and the goal is to hide Q. So I cannot just release the secret key in the clear because then, the whole point of obfuscation is to hide the description of Q. So just a QFHE scheme is not enough for me. The evaluator the goal is that the evaluator should learn the decrypted value of the unencrypted value of Q of X, as long as we have some proof that it didn't cheat or it performed this homomorphic eval procedure honestly. So as long as it performed this evaluation procedure honestly, it will get to learn Q of X, otherwise it won't. So that's why we need publicly verifiable QFHE. And what the scheme is at a high level is that, again, you encrypt your inputs the same way. So you're still thinking of evaluating some universal circuit, U sub X, and the client will encrypt the circuit Q with the public key and send over the ciphertext. And now the evaluation functionality would be different. So instead of just outputting CT prime, the server, when it evaluates the universal circuit on CTQ, it will also output a proof pi. And this proof pi is basically, this proof pi is saying that here's a proof that CT prime was computed honestly by homomorphically evaluating U sub X on CTQ. So this proof is sort of evidence that everything was done honestly, therefore I should get to learn, therefore you should decrypt the CT prime for me. So but the issue here is that I don't have a way of verifying whether this, I don't have a way of verifying this proof. So assume for now that I had a verification functionality which was able to do this. So in particular, it took the proof pi and all the encryptions. So it took the encryption of the circuit Q and it took CT prime as input and also the universal circuit. And it was able to correctly say accept if CT prime was computed honestly and reject otherwise. And now we only decrypt if this verification functionality accepts. So we only decrypt if ver accepts. If we had this type of QFHE with this additional ver function, then that would be enough for obfuscation. And in particular, okay, I'll explain that later. But does everyone agree that publicly verifiable QFHE is?
Yeah.
Okay. So for now, assume I have this verification functionality that I described earlier. How would I get obfuscation from this? So again, the obfuscator, there's some universal quantum circuit, and the obfuscator runs the keygen algorithms for the publicly verifiable QFHE scheme. It gets public keys and secret keys, a public key and a secret key, and then it encrypts the circuit Q with the public key. And And now we define this oracle C, which takes as input some instance X. So an instance X, I want to evaluate my circuit Q on. It takes as input some instance X, C tilde, some ciphertext, and a proof pi. And it only decrypts the ciphertext if the verification functionality accepts. So the verification functionality I described in the last slide. This C oracle will only decrypt if verification passes, otherwise it won't decrypt. And the output of the obfuscation will just be this oracle C and the encryption of the circuit Q. So this is all classical. And what would the evaluator do? The evaluator it will get this obfuscated circuit Q and say it wants to run it on input X. It will first like parse this circuit, and then it will run the evaluation, the QFHE, the publicly verifiable QFHE evaluation procedure on the circuit U sub X and on input this encrypted Q. And it will get some proof pi and C tilde. This is just from, once we have publicly verifiable QFHE, this is what the evaluation procedure would give. And then it will just run C on X, C tilde, and pi, and it will output the result. So it will learn Q of X if the proof was correct, if it did everything honestly, and otherwise it won't learn Q of X. So why do we need public verification and not just verification? That's because we give the obfuscation output includes this oracle C, and it gives it to the evaluator. So the evaluator is free to access this verification oracle. And in particular, the verification oracle doesn't need any secret keys. So I can, access C on malformed proofs and see what the output is. And so this verification and like this evaluator can access an unbounded polynomial number of times. And we want security even if this is the case. So, okay.
So maybe you already mentioned this, but I guess you need a specific type of QFHE where the evaluated ciphertext stays classical, right?
Yes. Yeah, because the client is classical.
Right.
And it will stay classical. In BKNY, it doesn't.
Right.
But
So like it's not true for any QFHE, you need like the specific.
no, this is the right. So this transformation from publicly verifiable QFHE to obfuscation, this appeared in BKNY as well. But if you want classical obfuscation, then you want the ciphertext to be classical in this. Yeah. Okay. Okay, so hopefully now forget about obfuscation. I'm just going to focus on publicly verifiable QFHE because if I had this, then I already showed you how we can get obfuscation, right? So it suffices to construct this verification functionality for the certain class of quantum circuits that perform some evaluation procedure, right? Okay, so the first implication, how publicly verifiable QFHE implies with the classical client, how it implies classical obfuscation of quantum circuits we just saw. And now let's see how this commitments with classical keys and public decodability, how this implies publicly verifiable QFHE with a classical client. So I should say that this is all so how do publicly decodable commitments give us this QFHE? This is mostly black box in the paper and for this talk as well. Because this kind of transformation from these types of commitments to publicly verifiable QFHE, it has appeared in a lot of works and eventually culminated in BKNY. But I will very briefly describe what happens. Okay, so assume I have some notion, some commitment scheme that is satisfying some notion of binding that I will describe. But assume I have that for now. What the client will do in the QFHE scheme is it will generate some public and secret parameters for this commitment, and it will send these public parameters to the server. And the server, recall that it wants to convince the client that it performed the evaluation procedure honestly. So what it will do is that as it's performing this evaluation, it has some state it's keeping track of, and it's going to prepare, we call this the history state, as it's performing this evaluation. And what it's going to be able to do, it's going to be able to prepare many copies of the history state of the computation it's performing, right? And then it will commit to this history state, which is a quantum state, using this commitment parameters it got from the client. And then it will send the commitment to the client. And then the client is going to generate some more parameters, which tell the server where to open this, in what basis to open this commitment. And then it will open it, and then it will compute pi. This is very black box. How this happens is very complicated, but as a template, this is what happens. And the commitment that I'm talking about here is the publicly decodable commitment that I will talk about in a bit. But basically you can think of this as the server prepares many copies of the history state, it commits to it, and using the commitment, it generates proof pi. And then the client, as long as the commitment satisfies some notion of binding, the client can check this proof correctly. So what I need is I need to construct these commitments where these public parameters are classical. And once I have that, then I can run this template from prior work, and I will get a publicly verifiable QFHE scheme.
By the way, in commitments, there's also usually a hiding part. Do you guys need hiding at all, or?
We can just need binding. Yeah. Because the client knows the input. So
Right.
it's
Yes.
yeah, we just need that we need some notion of binding, and I'll talk about that.
Yes.
Okay, so the way we go from these special publicly decodable commitments to publicly verifiable QFHE is very black box, but the only thing to keep in mind is that if I have a commitment of this form, then I can produce this proof pi from it. So from now, I will just focus on how we can construct these commitments. And BKNY, which is the work that we are dequantizing, they constructed publicly decodable commitments with quantum keys. And we are dequantizing that, and we are constructing this with classical keys. Okay, so
Can I ask a question?
yeah.
Like, previously you said like your obfuscation only works for circuits that is pseudo-deterministic.
Mhm.
Where do you use this property?
Oh, so this is used in this black box.
Like, how do you use it? So if it does not satisfy that property, what is it usually?
Yeah, so if it doesn't satisfy that property, maybe I think it's a bit hard to, can we chat offline?
Okay.
This is part of BKNY, which I think will be clear.
Okay.
But I don't want to, we can chat offline. Yeah. Okay. Okay, so commitments to quantum states with public decodability. So forget about public decodability for now. Let's talk about committing to quantum states. So what happens in a commitment? There's a verifier. It runs the keygen procedure to get commitment keys and decommitment keys, and it outputs the commitment key. And the prover, say it's holding some state psi, and it wants to commit to the state psi. So it runs some COM procedure with the commitment key on the state psi to get some classical commitment C. And it will also get some residual state psi prime after it commits. And it will give this C to the verifier. And at a later point in time, the verifier will ask the prover, open your residuals, like open in the Z basis or in the X basis. So open in the standard basis or the Hadamard basis. And there's some opening procedure for each basis that the prover will run and on the residual state, and it will get some string U in each case. And you can think of this opening procedure as a measurement outcome. So I'm like measuring my residual state in the standard or the Hadamard basis, and I'm getting some opening U. And then there's some decoding procedures. So the verifier will take these openings and it will decode them, and it will output a bit. It will either output a bit or bot. So you can think of opening a committed state and then decoding the opening as just directly measuring the state prior to commitment. Okay, and what do when I say, okay, so what is, when will such a commitment to quantum states be binding in the Z basis? It will be binding in the Z basis if it cannot output a U such that the decoding procedure first, it cannot find an opening U such that when you run the decoding procedure with U, it first decodes to B and then later find a U such that the decoding procedure outputs 1 minus B. So it has to be binding to one bit. It cannot be, it cannot output an opening which first decodes to B and then at a later point in time find an opening that decodes to 1 minus B, because we want to be bound to a bit in a certain sense. After we commit to a state, there has to be some notion of binding to a classical bit. And that means that you cannot find openings which decode to 2 different bits, right? Okay. And so this is a commitment to a quantum state. And what does a commitment to quantum state with public decodability mean? This means that it should satisfy a commitment like this. It should satisfy binding in the Z basis, even if the prover is given access to the decoding functionalities in the Z and the X bases. So even if I'm allowed to decode, I should still satisfy binding. So I still cannot find an opening U which first decodes to B and then later decodes to 1 minus B. Okay. So BK and Y, like the work we're dequantizing, they constructed commitments with such a strong, with like a slight weakening of this binding property from something called subspace states. And what are like just so what's a subspace state? So a subspace state is just take some random subspace S of F2 to the N, and the dimension of S is N over 2. And the subspace S is balanced. So let S sub 0 be all the vectors in S that start with 0, and let S sub 1 be all the vectors in S that start with 1. And when I say the subspace is balanced, I mean that the size of S0 is equal to the size of S1. So it has an equal number of vectors that start with 0 and 1. And the subspace state that's produced from this subspace S is just a uniform superposition over all vectors in S. And from some like prior work, this is just a fact to keep in mind for later slides. We know that if you're given this ket S0, which is a superposition over all vectors in S that start with 0, then we can use this state to produce a ket S1, which is a set of all vectors in big S that start with 1, if we have oracle access to the dual of this subspace. And this has already been shown in prior work. Okay, so are subspace states clear?
I guess AGKZ technically shows that from S you can go to S0 or S1, which also means that you can go between S2 and S1.
Yeah, but in the commitment you do get ket S, as you see. Like, yeah.
Right.
Yeah. Okay, so here, I don't know if you see already, but this ket big S, this is the quantum part in BKNY. They construct commitments from these subspace states, which are quantum states. And how do they construct commitments that satisfy the binding notion that I described earlier? Here's the commitment scheme. The verifier, it gets, it will sample some random subspace S, and it will prepare this state ket S, and it will give ket S, which is a quantum state, along with two oracles, O sub S and O sub S perp. And what is O sub S? O sub S is just a membership checking oracle for the subspace S. And O sub S perp is a membership checking oracle for the dual of S, which is S perp. And it gives these two oracles along with this quantum state S to the prover. And so in order to, like I said, like when you're committing to quantum states, you want some notion of binding to a bit. So for now, let's say that the prover starts with ket S, and it wants, it wants to associate S sub B, ket S sub B to the bit B. So how will it do this? Any suggestions? Okay, I'll say, so what it can do is it can just measure the first bit, right? Say it wants to commit to B, measure the first bit. If it's measure the first bit of this ket S state. If it's B, then it's all good. But if it's 1 minus B, then from this fact, because it has oracle access to the dual, it can switch to SP, right? So it can always just create this state for any bit it wants to bind to, right? Okay. So to commit to like a superposition of bits, it can use like S perp in a controlled manner to create like sum over B, alpha B, ket B, and ket SB, where SB is all vectors like that start with B. Okay. And now, okay, so like the prover performs an operation, and the verifier now says open the Z bases for me. And so what the prover does is it measures the state in the Z bases, and it will get some bit B and sub vector S in S sub B. Do you agree? Okay, and it will send B and S to the verifier. And the verifier, the decoding procedure is just output the bit B if this, because the verifier, it sampled S, so it can check if S is in SB. And it outputs a bit B if S is in SB. So this is not at all a binding scheme. This is not a binding commitment scheme. Does anyone have any guesses for why? So recall that binding means that I cannot first open to B and then 1 minus B. So, and this is, here I can. And I can do that because I still have access to the dual sperp, right? So what I can do is, I can prepare SB in the beginning, and then say I start with SB, and then the verifier says open in the Z basis. I can switch to S1 minus B using the dual, and then open to 1 minus B when I measure. Right, so this is not at all binding. Also, we didn't even send a commitment here, but what BKNY does to fix this is that they use a signature token to remove access to the dual. So after I've committed, after I've prepared this state, alpha B ket B SB, if access to the dual is taken away from me, then I cannot do this swapping attack. So BKNY has a way of revoking access to the dual after committing. After you commit, you need the dual to commit because you want to be able to commit to the correct bit. But after you've committed, it's essential that the dual access is revoked because otherwise the scheme won't be binding. So I could show you quickly, but if you believe me, we can move on to our technical contribution. I can show you how this happens, but we can also skip that.
So, okay,
Okay.
so I guess you use subspace states kind of twice, right? Because signature tokens you usually also use subspace states.
Yeah, but the reason you're right. But the kind of the main technical, so in our work, like to dequantize the signature token part, you just replace that with the generic OSS.
Right.
And all you need is just the unforgeability of the OSS.
Yes.
But the kind of the main technical argument happens when you want to dequantize this ket S, the commitment key, really, not the signature signing key.
Nice.
So that's why I'm focusing on this ket
Right.
S. So just believe me that there's a way to revoke access to sperp. And now assume that after the prover commits, it doesn't have sperp. So after the prover commits, it doesn't have access to sperp. So now, at least there's some hope that we can prove binding. It's not immediately broken. So I will skip these slides. Okay. So like I said, that if you revoke access to sperp, you can prove binding. So this is how BKNY prove binding for their scheme. First, they eliminate this obvious attack by including like alpha set a signature token. And then they sort of prove that this scheme where the prover first, to commit, it has access to the dual. But then after it is committed and send its commitment to the verifier, access to the dual is revoked. And then it cannot really open in both bases. It will only be able to open in the bases like it committed to. Okay, so, and the proof is complicated. I won't go over it, but what is our main technical contribution in this work is to make this commitment quantum, right? So the verifier, which is also our client, it needs to be able to like only send classical oracles and like there are no like quantum states. So what we will do is like okay, so first let me describe to you what the experiment is for security for BKNY, and then I will show you how to dequantize it with like one-shot signatures. So what's again, like the commitment key is just this ket S and 2 oracles. And the prover will commit to the state it's holding. Say it's holding some state psi in a register B, and it will commit to it. And the commitment has the same idea where for bit B, you want to map to SB, like I described before. And for any state it's holding, it can perform this operation in superposition using access to these oracles. And then, like I said, BKNY has a way of revoking access to the dual. So after it's committed, access to the dual is revoked. And now what the verifier will do is it will sample a bit, and if B is 0, it will do nothing. And otherwise, it will just measure the residual state in the standard basis. So this is a notion of binding that is equivalent to being able to swap between 0 and 1. And what BK and Y does is that they kind of prove security this way. So the verifier will either measure or not measure, and the prover has to guess whether it measured or didn't measure. And it's successful if it correctly guesses whether the verifier measured or didn't. And what BK and Y did was they proved that this is secure. So if the prover commits and then access to the dual is revoked, and then the verifier with probability half measures the residual state, and the probability half doesn't, then the prover should not be able to tell. So what they proved is that this is secure. So what we saw so far is, so this is this kind of phenomenon of because these commitments are generated using subspace states. So we call this revocable collapsing of subspace states. So, once you revoke the dual, the prover should not be able to tell if the state is measured or not. So the state's collapsed after revoking the dual. So it's called revocable collapsing of subspace states, right? And what we saw is that revocable collapsing of subspace states will give commitments to quantum states with public decodability with quantum keys, because this ket S here is quantum. Okay, and our main sort of technical contribution is that we show that this revocable collapsing property that I described before, this experiment is secure when you generate these subspace states using one-shot signatures. So we show that revocable collapsing of one-shot signatures implies classical commitments, the same primitive but with classical keys. Okay, so I will briefly describe what one-shot signatures are very briefly. So and then describe how we dequantize this commitment. So you can think of one-shot signatures as there's some generation algorithm gen, and A is some polytime adversary. A has access to gen. Gen will output some verification key and a signing key. So the signing key is a quantum state, and it's used to sign messages. And say that the adversary ran gen, and it received the verification key and a signing key. And with the signing key, it wants to sign a bit. But because the signing key is quantum, once it signs one bit and gets a signature sigma sub b, this signing key, because it's not a classical string, it's a quantum state, it should be destroyed. And the security property is just confirming this intuition and saying that it's intractable to sign two messages with the same key. So even for the adversary, even when the adversary is given access to gen, it cannot sign two different messages with the same pair of keys. Samples the keys once and then it tries to sign two messages with SK. That won't happen except with negligible probability. Okay, so that's what a one-shot signature is. And there's a specific construction of this primitive, which last year by Shmuley and Zandri, and we will use that specific construction. Our main contribution is to just use that construction to dequantize this ket-s. Right? So in particular, we proved that this one-shot signature that was constructed by Shmuley and Zandri, it satisfies the revocable collapsing property that subspace states do. So in particular, even when the prover is able to generate these subspace states on its own, instead of getting them from the verifier, we can still prove a similar property, which proves like that these commitments are binding, even in this case. So now here's the dequantization. So now instead of sampling a subspace S and then giving ket S to the prover, the verifier it samples 3 oracles, P, inverse, and D. And this is from the construction of Shmuley and Zandri. I won't go into it, but that construction is in the classical oracle model. So these are the 3 oracles that the verifier samples, and it gives to the prover. P and P inverse, these are the oracles that the prover can use to generate these subspaces. So in the previous setting, it got the subspaces from the verifier, and now from this construction, it can use P and P inverse to sample these subspaces S. And this oracle D, it functions as a membership check for the dual of the subspace that the prover samples. So it's so the main difference is that the prover is getting to sample these subspaces itself, just with classical oracles. So now the commitment key is now these 3 classical oracles. And the prover now will use these oracles. Like I said, it will generate some S sub y. And then at a later point in time, the dual oracle will be revoked using ideas that are similar to B and Y. So it will be revoked, and then
So this time for revocation instead of the signature token, you use OSS.
yeah, we just use OSS, but
That part is like black.
yeah, we don't use the Shmuley-Zandri OSS. We just use any generic OSS. Yeah, because we only need the one-timeness for that. Yeah. So yeah, so D is revoked in exactly the same way as B and Y revokes their dual. And now the verifier will do the same thing it did in the binding experiment for B and Y. It will sample a bit, and based on the bit, either if it's 0, it will do nothing. Otherwise, it will measure the state in the standard basis. And the verifier's task is, and the prover's task is to guess the bit B. So the prover outputs some B prime, and the experiment outputs 1. So if B prime equals B. And what B shows that this experiment is secure. So the probability that B prime equals B is negligible. And I should say that this is not at all black box, because the one-shot signature that SC constructed, they prove that this they constructed it using hash functions, which satisfy collision resistance, but they're also not collapsing at all if you're given access to the D oracle. What we show is that if you revoke access to D, then they indeed are collapsing. So you cannot distinguish between measurement and no measurement if D is revoked. And what SZ25 shows that they're collision resistant, and you can distinguish with the D oracle very easily. So I won't go at all into how we prove this, but it's just by opening up this proof and it's proven in a very white box manner. Okay, so let me back up and say like what we've done so far. So we proved that this experiment is secure. So we showed that these one-shot signatures, this particular construction, it satisfies the revocable collapsing property. And this implies that we get commitments to quantum states with public decodability and with classical keys, because the keys are just now the classical oracles from the OSS construction. And from the black box part, that I described a very rough template, how these commitments give publicly verifiable QFHE. This gives publicly verifiable QFHE with classical clients, which eventually just gives you classical obfuscation of quantum circuits. Yeah, and just to emphasize that our main technical contribution is to show that the one-shot signature construction from Shmuley and Zandri satisfies this revocable collapsing property. Yeah, and I'll just end with a couple open questions. So we're following we're following BKNY like the roadmap and everything, and we're dequantizing BKNY, and BKNY is for pseudo-deterministic, is obfuscating pseudo-deterministic quantum circuits. And we dequantize that, but can we get a classical obfuscator for other functionalities? That's one open question. And this is all in the Oracle model still. So can we make this construction plain model or other obfuscation constructions plain model? Yeah, thank you.
Thanks. Do you have any questions here or on Zoom? Do we have any questions on Zoom or?
No,
No.
version.
So I'll ask one question. Can you go back one slide? So this last part from public verifiable QFHE to obfuscation, that's like the, I guess, most natural and straightforward part.
Mhm.
But when you're formalizing that part, are there any challenges there, or is it straightforward?
No, it's very straightforward. It's even like, I think, folklore from classical. Like,
Nice.
yeah, the only kind of the only, I think, complicated part is to go from commitments to publicly verifiable QFHE, but that was in BKNY. They kind of established this, and
I see.
because we're following kind of their roadmap, it suffices for us to get these commitments of classical keys.
See, so that part is generic enough so that when you plug in like classical keys
Yeah.
on this box, you get like classical.
Yeah, because it's just the keys are just the client's ciphertext. So it's yeah.
Second question. So I guess in the plain model, like most of these steps stop working, right? They're like very Oracle dependent.
Yeah, and in particular, like this revocable collapsing game, this revocable collapsing, it only makes sense. Like, well, I don't know how to define it in a plain model because I'm
You
taking.
cannot just take away their key.
Yeah. I'm taking away, or I'm like revoking Oracle access. I'm not taking away the Oracle, but I'm effectively taking away the Oracle by the signature token. So with IO, I don't think this is even the right definition.
Nice.
Yeah.
The other steps, can you?
Yeah.
Steps again. I see. Probably the last step is plain model friendly, I would say. As you said, like I think even in the classical setting, they do this in the plain model.
From
QFHE to obfuscation. I guess it depends on the particular FHEs.
Yeah, I think so.
But at least that part is like a known classical like plain model counterpart.
Yeah, the transformation is very well known.
Thanks. Do you have any other questions? Okay, let's thank the speaker.